So let me do some introductions then. I'm Callum Hackett, and I'm the head of research at Unlikely AI. And so I lead our Unlikely AI Lab, which is a dedicated arm of the business which focuses on research into explainability methods and trustworthy AI. And for the webinar, I'm joined by a colleague of mine, Matt Bongiovi, who is a research engineer. And we also have a guest speaker, Francesco Leofante, who is assistant professor at Imperial College London and co-director of their Centre for Explainable AI. And I'm just going to hand over to them to give us a 1-minute introduction of their backgrounds and their route to the conversation today. So let me start with Matt. Could you tell us a little bit about yourself?
Yeah, absolutely. Thanks for the intro. I'm Matt. I am a research engineer here at Unlikely. I've been around on the project for a couple of years now and worked across various efforts that we've had, both on the research side and on the product development side. And a lot of my focus is on making sure that the research breakthroughs that we have do end up into the products, and that the work that we're doing on the product side helps inform and provide requirements and data and all of those things to the research side. And my route to the explainable AI element of the talk is that a lot of the work that we've done in the past within the umbrella of trustworthy AI sits within how do we make these systems that are explainable for users. And that's me. I'll pass to Francesco.
Thank you. Hi, everyone. My name is Francesco Leofante, and as you already know, I'm an assistant professor at Imperial in the Department of Computing, and I'm also co-director of the Center for Explainable AI. Now, my research mostly focuses, perhaps unsurprisingly, focuses on explainable AI. And during the last few years, I have worked on different techniques, mostly, developing algorithms and studying fundamental properties of explanations for machine learning models, starting, going from predictive AI to generative AI. I've looked into a little bit of everything. And on top of that, I'm also interested in symbolic AI. So, it's kind of an interesting mix of, good old-fashioned AI and new trends.
Great, thank you very much. And as for my background as well, I'm split between academia and industry. In a past life, I lectured in linguistics and philosophy and was particularly interested in the evolution of language in the human species. And so I ended up coming into AI, but I've always been interested in questions about intelligence and language and reasoning. So I'm going to get us started with our main theme of explainability then. So I can say that Matt and I particularly benefit from working at a company where explainability has been a core principle for its entire existence. And as Francesco just described, he's worked in a few domains in AI research, but I think explainability has been a key issue in each of them. Now, obviously, when we look at the industry landscape, if you just think about the first sorts of AI products that might come to mind, explainability doesn't really get top billing if it's featured at all. But I would say that I feel like there's a mood shift happening in the industry at the moment. I think kind of in the past year, but I would say especially even just the past 3 months or so, the more I look at the conversations people are having, the more I see trust as a major issue and explainability as a major issue. And I think it's probably no coincidence that this is happening around the same time as arguments against the limitless potential of scaling LLMs are gaining ground. And so just with that background, Francesco, I wanted to ask you from your perspective, why has explainability been a key issue for you in your research? And do you have any thoughts on the increasing interest we're seeing from other places in the industry?
Yeah, so explainability, I actually I started working on trustworthy machine learning coming from safety, right? Instead of explainability. So I'm an engineer by training. So my first approach was, okay, let's try to verify machine learning models and let's try to make sure that they do satisfy basic functional requirements, right? But then soon after that, I actually realized that explainability is potentially as important as verifying safety, right? If you have a model that is provably safe, it does what it is supposed to do, but then you cannot explain the outputs of these models, right, to people, to us, right, to humans using the model, then it's pretty obvious that even if you have, as perfect as a model can be, it's not going to be used, right? Nobody's going to trust the model. Nobody's going to use it. For that reason, I started to work on explainability. And that was kind of one of the motivations. And as for the second part of your question, I think I completely agree with you, right? On the motivation, right? Why is XAI becoming so, well, important, or anyway, a hot topic now? It's been a hot topic in the research community for a while, right? I think, going back, I don't know, even 2017, 2018, people were already actively working on the topic. But now when it comes to industry, I actually think that the widespread adoption of LLMs, right? Or anyway, the way in which these models are now part of our daily life, right? We all use LLMs or have used sometimes, LLMs for tasks, from writing an email to something slightly more complex, perhaps coming up with research ideas even. But now that we're all familiar with this technology, we're also very familiar with the limitations of it, right? And I think precisely because of that, everybody's kind of started to realize that maybe it's actually better if we try to explain how these models come up with their recommendations or with their outputs, generally speaking. And I think perhaps that's the main motivation, I would say. And now that these things are actually, now that people like you guys, for instance, are looking into turning these fantastic, amazing AI solutions into products, the reliability, transparency, interpretability issues, they become even more pressing.
Yeah, exactly. I think, Matt, from your perspective as a researcher, then you think a lot about the need for explainability for end users. Could you say a little bit about that from your perspective?
Yeah, definitely. Yeah, I think there certainly is this element that Francesco was just mentioning of the taking these things and getting them adopted, and trust being a barrier to adoption. But I think there's also an element of uh, what does a user need in order to be able to do the things that they want to do? And I think that is different depending on the use case that you're in. One of the distinctions that we might see is that there are use cases where there's like this co-pilot use case where people are working alongside a piece of an intelligent system, and they need to more thoroughly understand things about how that system is arriving at its outputs, so that they can work alongside it effectively. Um, and I think that forms one uh, key element for building products that users can use effectively.
Nice. I think as well, I mean, something very concrete which we've seen just this month is that the Australian government has banned social media for under 16s, right? And that's not exclusively an explainability issue, because there are all sorts of things that have informed that choice. But certainly one of them has to do with the dangers of content recommendation algorithms, for example. And that's a prime use case for ML techniques where I think people have just accepted by default that there's no explainability there, but there's no in principle reason why you couldn't have that there. And so I think there's a degree of short-termist thinking in not building for explainable use cases. And also just building on something you said, Francesco, about the motivations for like bearing in mind the limitations of the systems that we've scaled so far. I think there is a slight tendency to mistake explainability for a niche issue than it really is, as if it were only to do with concern for harms to end users. Because while I think that is an important issue, explainability gives everybody who interacts with AI leverage over those systems. And it doesn't matter if you're a user or you're a developer. The more you understand, the more you can improve the things that you're building. And I think it's been interesting for me to see even the so-called reasoning models that the big model providers have created are much more capable on certain tasks, because although the reasoning tokens that they generate when they're thinking are not like genuine descriptions of how those models are working, just the fact that you make something that looks like a reasoning process an artifact that the model can look at creates a kind of meta reasoning process where you're reasoning about reasoning, and it opens up the space of potential solutions you can develop. And that is what explainability AI opens up itself as well. You just have paths to completely new kinds of reasoning when you can reason about how the models work. So I think the motivations for explainability are very substantial, but I also know from personal experience that explainability is quite a high level concept that means different things to different people. And I'd like us to start with the perspective of regulators who are pushing for explainable AI systems. And so, Francesco, I know you've recently partnered with Ofgem, the energy regulator, for example, and you've spent some time looking at explainable AI in the context of energy and critical infrastructure. Do you have any insight into how regulatory bodies are thinking about explainability, or are you perhaps helping them define even what they should be looking for in that space?
Yeah, so I think starting, I agree with you, explainability is very broad, right? And it means different things to different people. You picked the most challenging one, right? Regulators, because it's really an open problem at the moment, right? Because on the one hand, we are trying to, we as in not me particularly, but people are trying to use AI, right, in different sectors, including the energy sector. But that in itself is kind of is a challenge, right? So there is no obvious, of course, there are established AI solutions that are being used in the energy domain, forecasting, for instance, and other things. But reasoning about the limits, right? Defining the limits of AI when it comes to applications that are, consequential, safety critical, high stake. This is very difficult, right? And this is something that the regulators have only recently started to look at, right? Perhaps, I mean, it's not yesterday, right? But maybe the last couple of years, right? And there's actually not much out there, right? So what I am doing as part of my job is to actually team up with people who are expert in policy and regulation, and sort of try to come up with first of all, try to establish a common language, right? Because I think that's actually the first barrier. But then, from this common language, hopefully, it will take us some time, but hopefully we will manage to also come up with some some ideas, right, on how to effectively regulate the use of AI without stifling innovation, right? Because you still want to use AI. If there's if there's something AI can solve, then I guess we should probably explore those opportunities. But at the same time, we should make sure that whenever we deploy AI, we are in control, right? And I'm not talking about AGI kind of existential risk, or this kind of, in my view, slightly more philosophical questions. I'm really talking about concrete problems that might stem from using AI in a way that, perhaps a bit too lightly, right? Without necessarily having figured out all the potential challenges that might arise.
And Matt, I know that you've worked in other industries, such as finance and insurance, for example. Could you tell us a bit about what you found of the attitudes of regulators in those domains?
Yeah, I think in a lot of cases, regulators are, as Francesco was saying, they're providing a broad set of guidelines without necessarily defining specifically what implementations are compliant and what implementations aren't compliant. And to know the answer to, is my system that's produced this explanation, will that fulfill the obligations that I have under this regulation? That's a hard thing to know. And because we're so early in the process, we've just really not had that public debate and discussion around what things are compliant. I think one of the things that's interesting is, I think regulation is incredibly important, especially in these high risk areas. But you almost have this other lever, which is what we were saying before around the user experience constraint. And I think regulating explanations for AI is hyper important when that user constraint doesn't exist, because there are plenty of use cases where we deploy AI systems and users don't necessarily have a choice that they are interacting with it or not. But there are plenty of cases where they do have a choice. And if users are not finding it useful or finding that it's not something they can trust or not something that they can understand, they can just walk away and not use the tool. So in the building products for like finance and insurance, we have this extra constraint, which is that we need to make it useful in a way that will keep users using it. And that means understanding what they need to know, understanding how we distill the information that we have uh, so that they can understand it and so that they can operate over it.
Right. So I think then we've developed sort of two important but different perspectives, the regulators and the users, where the regulators will typically be thinking ultimately about the impact on users, but really trying to avoid adverse effects. Whereas, as you just said, Matt, there are all sorts of other concerns that users themselves have to do with usability. Um, and so perhaps, Francesco, I could also ask if we've got this perspective of the regulators and we've got the perspective of the users, but we think about ourselves as researchers and engineers. Do you think explainability means anything else additional to you? Because I guess presumably explainability methods are a key enabler of the research you do, and there are all sorts of insights you have that might get filtered down by the time you're talking to regulators, for example.
Yeah, that's very true. In fact, right? Because when we do as researchers, right, when we develop new methods for explainability, for instance, we or interpretability, we look at properties that may not be necessarily or immediately relevant to regulators or even end users, right? If you think about one big area of research, which is mechanistic interpretability, for instance. These kind of all the research that goes on in that area mostly looks at internal mechanisms, right? So the internal mechanisms that models such as LLMs sort of leverage to produce their outputs. But now these internal mechanisms, they may be important for us, right? Model developers, for instance, we could leverage on that information or on leveraging the information that is provided by those explanations to better understand the reasoning of these models. But I doubt sort of a lay user would actually care about even about what activates in layer 15 of a transformer, right? So there's a lot there, right? And explainability is an exciting area of research precisely because of that, right? Because there is basically a spectrum of explanations and ways in which one could actually think about generating explanations and how these explanations could be used. There's so much to do there, right? So yeah. And I think when we talk about regulators, for instance, and regulating AI, and when we think about the role of explainability in all this, we're just at the beginning, right? We just started. I saw there was a question in the chat that was asking about what regulators think when it comes to now I don't want to misquote, but yeah, when they ask for explainability, do they know what they're asking for? To be honest, the answer is sometimes. Sometimes they do, sometimes they don't. But it's also, I mean, it's fair, right? Because I think this is an exercise that we should all do together, right? Like all the stakeholders, academic stakeholders in this industry, industry players and regulators as well. We should all sit at the table and sort of try and discuss, what it means to regulate AI, what it means to use explanations to whatever, make sure that AI outputs are compliant with regulations. This is clearly not it's not a trivial exercise, right? It's not, and there's no simple answer, and there's no single explainability method that works. And I think, as Matt was saying, there are so many different scenarios, so many different use cases, right? And different XAI techniques might be, they might work for some use cases, but not for others. It's so complicated.
Very complicated, but I think you put that very well. I completely agree. So now that we've got a feel for the landscape, let's dig into some methods then. And so, Francesco, I'd like to ask about some more of the details of your ongoing research. Could you start by telling us about the difference between anti-hoc and post-hoc explainability, and then define counterfactual explanations in broad terms for people who are not familiar with the idea?
Yeah, sure. So let's put it this way. Historically, at least, there have been sort of two different schools or two different ways to explain the decisions of machine learning models, mostly. The first is, as you said, anti-hoc. That basically boils down to building models that are interpretable by design. Okay, so that's a situation where you develop say, a machine learning classifier whose decision logic, whose internal reasoning process is auditable, and it's kind of almost human readable. Think of a decision tree, for instance, a small one. You take a small decision tree, you can actually start from an input, and then you go down the tree, you traverse the tree. At each node, you see what decision is being evaluated, and then you go all the way down to the leaves where you can actually see the final decision, right? And this is a model that is called interpretable because you can really understand what's going on, right? But then, of course, as you move towards more complex models, which could still be tree-based, but imagine just having a lot of them, right? You have a random forest, or you have a neural network now, right? Where, to be honest, sometimes it feels like their outputs are just produced, there's black magic going on in there, right? They do amazing things, but we're not entirely sure. Sometimes we really don't know how that given output has been produced. Now, when it comes to these models, that's where post-hoc explainability techniques can be used, right? And post-hoc explainability means, can we generate algorithms that take the model already trained, right? And try to figure out the mechanisms, the sort of the logical, if you will, the logical pathways that led to specific decisions for specific inputs, right? And now I'll try to keep it short, but then of course, when we try to generate these explanations post-hoc, we can try to look at local behaviors, we can try to explain global behaviors, and counterfactual explanations, given that you mentioned them, first of all, counterfactual explanations is my passion, right? This is what I've been working on for the last 3 years. So, there's, of course, big fan. But counterfactual explanations are one example of post-hoc explainability techniques. They are local in that they try to explain the behavior of a machine learning model for a specific input, right? And to give you a concrete example, counterfactual explanations are typically used to generate recourse recommendations for users that have been negatively affected by the decisions of a machine learning model. Now, think, for instance, of a neural network that has been used to predict whether a person applying for a loan will be able to repay their loan within the given term. Now, suppose that the neural network says no for this specific person. Now, how can we help the person sort of change their application for the loan to be accepted? And this is what a counterfactual explanation can give you. Slightly more technically, what a counterfactual explanation does in machine learning, it looks for minimal changes to the input of a machine learning model, such that the machine learning model kind of flips the prediction with respect to the original input, and typically produces a desirable prediction for the user, right?
So if I can just say, Matt's got a visualization of this for us, so
yeah,
you can talk us through it further as we show that, so people have a aid. Yeah, sorry to interrupt. Keep going, Francesco.
That's okay. There you go. Yeah, that's exactly what a counterfactual does, right? So in this example of a loan application, if you look at the black cross, that's the original input, right? So there's a person, 25 years of age, applying for a loan of $15,000 with a salary of 20K. And now the neural network, assuming it's a neural network for this, it doesn't really matter for, as far as counterfactuals are concerned, but let's assume it's a neural network. The neural network classifies this input as, as a sort of in the red portion of the input space, so the loan is denied. Now, a counterfactual is, as I was saying, a minimum modification to the input, which would basically cross the decision boundary. Okay, so formally, counterfactual explanations are typically computed by solving the optimization problem that you see at the top of that slide, which basically means give me another x prime, give me another instance, which is as close as possible to the original one, which is the cost bit, such that the output of the classifier f theta flips. Okay, so you want to obtain you want the predictions for the original point and the counterfactual point to be different. Now, of course, there are many ways in which there are many counterfactuals, so to speak. In fact, counterfactuals are not unique. And what we see on this slide is the difference between a counterfactual that is minimal in cost, so minimum distance, and a counterfactual that is not. And this is one of the main metrics that are used to evaluate counterfactual explanations in XAI research. And what you see here is that basically cost is used as a proxy. What you see here on this slide is that a counterfactual that is not minimal in distance might end up suggesting changes that are not feasible for the user, right? If I have a user whose salary is 20K, of course, if their salary could increase by 80K, the loan would be accepted. But maybe, in that scenario, they wouldn't even need a loan anymore, right? So we still need to make sure that these counterfactuals are feasible and usable in practice, and that's kind of what counterfactuals try to do. Or anyway, these are some of the properties that counterfactual explanations typically try to optimize for.
Excellent, thank you. And I think, Matt, if you go to the next visualization as well, one of your major research themes, Francesco, has been about the robustness of counterfactual explanations. And on this slide, we've just got a collection of different decision geometries, I guess. So you don't have to walk us through all of these by any means, but could you just give us a flavor of what sorts of issues these are representing?
Yeah, so the point is that when you try to generate if when generating counterfactual explanations, you only care about minimality, right? You end up generating counterfactuals that lie on the decision boundary or very close to the decision boundary, right? And then depending on the geometry of the decision boundary, as well as other sort of challenges such as fine-tuning or models that are not static, right? Models that evolve over time because of fine-tuning, as I said. Anyway, anything that can change the geometry of the decision boundary, or depending on how the decision boundary looks like to begin with, you might end up generating explanations that are very brittle, meaning that you change something either in the inputs or in the model or in the counterfactual itself, and all of a sudden you are left with an explanation is not valid anymore. For instance, I'll just give you one example. If you look at the top right corner, what you see there is an example of lack of robustness to input changes, which has actually interesting and important consequences when it comes to fairness of counterfactuals. What you see there is the two black crosses are two inputs. They're very similar. They lie close in input space. The neural network classifies both of them as rejections, okay? And now what you do is, if you compute counterfactual explanations that only look at minimizing distance, you will end up with two explanations, two very different explanations, right? The first input, or like the topmost one, gets the black dot, and the other one gets the white dot. And now this is just an abstraction, right? So this vignette doesn't necessarily convey sort of the severity of this issue. But now imagine a situation where these two inputs are basically the same profiles, and they only different, and assume that these two inputs only differ on one protective feature, for instance, right? Now, in this situation, you would end up having two very different explanations for two individuals that are very similar, except for this one protected feature. And you might end up, and in fact, my research, as well as the research of others, has shown that you can actually end up generating recourse recommendations based on counterfactuals that are effectively discriminating subgroups, right? So this is kind of one of the many problems that can arise when when generating counterfactual explanations, if sort of, if we're not careful enough, right? If we do not make sure that our counterfactuals are robust and trustworthy. And this is actually a very interesting problem, more generally speaking, right? Because if we're advocating for XAI, explainable AI, as a tool to effectively, open the black box, as they say, and sort of help us understand the decisions of machine learning models, then we actually need to make sure that these explanations are capturing actually capturing the decision process, the decision making process of a model. So they need to be faithful. B, they need to be reliable, right? You don't want to have an explanation that is brittle and breaks, sort of as soon as you change sort of a little bit, in the input, for instance. So this is kind of robustness in 1 minute.
Thank you very much. And I'd love to talk as well about the application of the method to different types of models. And I see that somebody asked a question about that in the chat, but I think we'll try to make time for that in the Q&A segment so that before we finish, I can bring in Matt to talk about something else that we've been working on at Unlikely AI. And so earlier we made the distinction between anti-hoc and post-hoc explainability methods, and we've just seen counterfactuals as part of the post-hoc category. Matt, could you tell us about something we're calling pre-computed reasoning and why that belongs to anti-hoc methods, and perhaps connect it to other approaches in the neurosymbolic landscape?
Yeah, definitely. So Francesco was mentioning earlier that when you're thinking about these anti-hoc methods, you can think about deciding upfront what the decision process will look like, and then codifying that in some way. And then when you're actually doing an evaluation or passing data through the model, what you're doing is going through that pre-computed reasoning, that like reasoning that you established upfront, and maybe you're evaluating certain things within the boundaries of that decision process. But at the end, you have something where you knew exactly what the decision process looked like, and you can then explain using that auditable decision process how you arrived at a specific result. And I think people who are familiar with what Francesco was mentioning, like decision trees or even like expert systems or rules-based systems, these typically have this exact design where you know what steps you're going to go through, and maybe you can conditionally move through them under different data inputs, but you have a way of tracing back exactly what you did to derive a result. One of the things that we think about here at Unlikely is neurosymbolic methods that let us take these structured symbolic rules-based systems and pair them with the more statistical models that we were talking about at the start. And how do we strike a balance between the trade-offs of the robustness, explainability, but also inflexibility of these structured reasoning processes? How do we balance that with the much more flexible, but also slightly more error-prone or slightly more unexplainable elements of more statistical machine learning models? And you see these neurosymbolic methods are, I think, becoming more and more popular. And there's work with like AlphaProof from DeepMind, where they were basically constructing language models that could produce structured steps within Lean, a proof writing language. And then you can get the robustness of the sort of proof solving systems, while also having the more generative elements of constructing steps in the proof process and testing those and being able to arrive at results with a balance of the neuro and the symbolic.
Right. So in this domain, the possibility of using a symbolic representation like that, and also the shape that it will take, is very strongly informed by the particular problems you're working on. So I think you've also got a visualization for us,
Yes.
which will help you talk through the work you've been doing on regulatory documents in finance, for example.
Yeah, that's exactly right. So if we look at this tree here, and actually it's important to note that this is not the formalization of a decision tree that one would typically think of, and what Francesco was describing earlier, where you might start at a root node and work your way down through this process. This is more of a criteria tree that represents similar criteria to the loan example earlier on. And basically what it's trying to do is specify in a somewhat logical formalization what it means to say that someone can get a loan. And there's the criteria that they must be 18 or over. And then also there's a couple of different options for getting a loan depending on the balance of their savings and the loan amount that they're requesting. And one of the things that we've been doing, and the sort of pre-computed part of our term pre-computed reasoning, is we want to derive these things in a way that is scalable and using existing non-formal specifications of some of this logic. So this is a very small toy example, but you could imagine maybe you have an insurance document that indicates criteria for how you would specify whether someone is covered for a policy claim under that policy. And there's already a unstructured description of what the criteria are, and we want to, as a one-time operation, compute a structure that would allow us to then do a mixture of symbolic and neuro evaluations, where symbolic is just propagating logic through this tree in the way that's quite obvious, and also evaluating these kind of leaf nodes for whether they're satisfied or not given some piece of unstructured information. Um, and again, I think this strikes a nice balance, or we've seen it striking a nice balance between the structured and explainable elements of a symbolic system with neurosystems where it might not be that obvious given a piece of input data whether you can classify a person as being over 18 given that input data, but you can use statistical models to help fuzzy match basically a piece of input data to a result or a yes/no label for that node.
Nice. And as Francesco was saying earlier, with anti-hoc explainability methods, in theory, you've got an easier application for explanations because the explanation is kind of implicit in the computation itself. But, you might consider that just as you run this as a software program, and then the execution traces are your explanation, as it were. But that's not going to be digestible to a user of this system. So I think you've also got an example just to give people a sense of the scale of some of these graphs that we might produce. Could you also talk a little bit about some of the engineering that's involved in converting these to what a user would regard as an explanation of how the system works?
Yeah, definitely. I think if we look at this, it's like we said, a toy example, and it's quite small. So it does become very easy to say, if there's a node that we could change in here to arrive at a different result, what node is that? That becomes quite simple. But if we're looking more at like the actual scale of the documents that we're processing, this is sort of one section of one document from an insurance policy that we operate over. And you can see it's more like on the order of about 500 nodes. So determining the set of alternative realities, which becomes basically 2 to the n on all of the nodes in this tree, that becomes impractical to present to a user that says, here's how we arrived at your result. Here's all of these 500 node labels, or even here's like many alternative pathways through this tree that would have gotten you to a different result. That becomes unusable for a user, as you were saying. And one of the things that we tried to do is find ways to reduce down the set of subtrees that are actually relevant to a specific query. And we can do that by lots of different methods. You can establish priors over some of the nodes so that you're not evaluating things that are unlikely to be relevant to a user, and you are evaluating things that are relevant. And you can also select how the order in which you evaluate some of these nodes can also provide you some leverage in terms of getting to an explanation that's usable and digestible for a user.
Perfect. So we are heading towards the Q&A segment in a few minutes. And so I'd encourage people to post questions if you haven't already, but we're certainly going to go back and review the ones that are already there. But while people are posting questions, just to round off the conversation, I'd like to expand a little bit more on the usability of explanations. And Francesco, one of the things that stuck out to me in one of your papers was the understanding that for a user, in essence, having an explanation is only half the battle, because you also have this notion of contestability, which is partly about what a user can actually do with that explanation in practical terms. Could you talk a bit about contestability?
Sure. Contestability has to do with this idea that so when a user interacts with an AI model, this rarely happens as a sort of just one shot kind of interaction, right? So if I'm applying for a loan, I'm submitting my application, and then the machine learning model says yes or no. But now, suppose it says no, right? Then the user might want to ask why, right? Why am I not getting the loan? Or what should I do to get the loan, right? And then you could use explanations to answer this question. But now, suppose the user disagrees with the answer that has been produced by an explanation method, right? Just to give you a concrete example, if the user asks why, then a feature attribution method might say, well, look, because this feature here might be salary or something else, was critical in this in steering the prediction towards a negative outcome. But then the user might say, oh, but wait a minute, there was this other piece of information that I did not integrate in my application, right? But if I did that, like, how would your decision change, if at all, right? So contestability it's kind of the idea that the way in which we interact with machine learning model and, focus on interact is not just this one shot sort of yes or no situation, which we typically consider in papers, in research papers. Typically, we tend to simplify, like, things have changed and are changing, but for a long time we we are computer scientists after all. So the focus was only input output behavior, one step. But contestability is this idea that we should really go beyond that, and we should actually design our AIs in such a way that users can effectively engage in this contestation process, right? So that they can actually and hopefully truly understand what the AI is doing, what the AI is thinking, and sort of how the AI actually reached the conclusions it did. And mind you, contestability and redress, they're one of the 5 AI principles that have been set out by the government in the UK, right? As part of the strategy for sort of a safe development of AI. So this is kind of a very interesting area which we have only started to explore recently, maybe in the last year or so. So that's quite exciting.
Yeah, I think certainly for me, one of the things that helped crystallize in my mind was that even if you've got a system where you're really confident in the explanations it generates, often to make an explanation usable, you have to make all sorts of assumptions to surface the one fact that you think might be actionable for the user, for example. But there's always a possibility that the assumptions you've made are false or just fallible in some other way, which means you can't really think of an explanation for the system as some static thing that you have for each input-output pair. It has to be an interactive dynamic, because the way that we understand how these decisions are made in complex systems requires conversation, essentially. It doesn't matter how the model works, whether it's humans or a model. Conversation is how we understand each other. So thinking about questions then, there was one that I saw earlier, which I particularly wanted to get to on the topic of counterfactuals. And I was interested to hear from you, Francesco, on the scope for it applying to different sorts of models. Because, for example, I saw a very interesting paper recently where counterfactuals were being generated for a classification model for ECG graphs in a healthcare setting to help increase trust in the way that model was using. But I think it's much less straightforward to try to apply counterfactuals to LLMs, for example. Could you give a taste of that landscape?
Yeah, sure. There are many challenges, right, when it comes to LLMs. I see one of the questions mentions the number of parameters, right? But that's actually not the only challenge, or not the first challenge that comes to mind. defining counterfactuals for language is difficult, right? And it's good that we have a linguist here because that's kind of all our examples focused on tabular data, right? Or at least that was the assumption. When you deal with loan applications, you have numbers, right? And the worst that can happen is that you have categorical features. Oh no, how do we deal with that, right? But now when it comes to language, things are completely different, right? So now, concretely, there is work on generating counterfactuals for LLMs, but the techniques are actually different, right? They do not follow or they do not try to solve that optimization problem that we had in one of the slides earlier, right? That's not the approach that is used for LLMs. Typically, the way in which people generate counterfactuals for LLMs is by directly querying the LLM again, right? Trying to generate natural language explanations, natural language counterfactuals, right? And that's where the whole work on chain of thought reasoning and related techniques sort of come into play, right? So that's how people are generating counterfactuals for LLMs nowadays. Of course, there are some challenges there. One of them being LLMs can hallucinate, and if they can hallucinate in their original predictions, there's nothing preventing them from hallucinating on the counterfactual as well, right? So this is a very interesting area of research. What I'm looking at the moment is ways in which we could actually look at the latent representations of these models and potentially try to generate explanations from those representations, right? Hoping that this will increase the validity and consistency of explanations. But yeah, I hope this answers the question on size. I see there's also another one on complex models and adversarial examples. Yes, the original formulation of counterfactual explanations was in fact PGD, right? So there is this paper in 2017 that was, to my knowledge, the first one to put out this notion of counterfactual explanations as solutions of an optimization problem. If you look at the optimization problem, which is the one that we had on the slide, it's really just an adversarial attack, right? Which is why these explanations sort of, if you only care about minimizing cost, you might end up generating explanations that are actually attacks, and you don't want that, right? So there is research showing how how close counterfactual explanations and attacks can be in the naive setting, so to speak. There is research on improving these counterfactuals, including work that I've done. Sort of, just to give a sort of a very quick summary, what happens is that if you start focusing on the robustness and plausibility of these explanations, you push counterfactuals further away from the decision boundary, and you end up aligning a bit more with the data manifold. And this has the effect of increasing robustness, but also increasing the plausibility, as I said, of these explanations, and sort of reducing, loosely speaking, reducing the similarity between counterfactual explanations and adversarial attacks.
Excellent. I think that first answer as well definitely addressed the question about LLMs. Matt, I think when you were showing the pre-computed reasoning graph, we also received a question about the example having nodes which were binary true or false, and whether you could talk about examples that aren't as straightforward.
Yeah, definitely. And I think we typically will treat these node labels as like a binary true, false, or non-determined, so that we can capture the cases where we can't easily do this like fuzzy match between our evaluation of that node and the data that is the input to the system. But the end result is that the root thing that you are deciding is typically a yes/no decision. Um, we have done work to try to massage that a little bit and have it not necessarily be just a yes/no decision for whether a piece of input data fits the criteria for some decision, but we might also try to define these as, for example, a set of obligations that come out of a regulatory document that we've maybe used as the source for the reasoning that we're then structuring in this way. And in that sense, what you're getting out of each of these like reasoning traces is still a binary, like is an obligation applicable to a specific scenario? Yes, no. But that then serves as like a springboard for doing other kind of things where an obligation might be met in many different ways. It might not just be as simple as a loan being granted or denied. Um, and figuring out how to ensure that a separate input is compliant with a set of obligations is another area of research that we've done work in, and gets a little bit more in this direction of not simple binary classifiers.
Thanks. And we also received a question from Melinda about whether explainable AI in practice, if not properly implemented, could exclude certain minority user groups. Now, obviously, we saw from an example that you gave earlier, Francesco, that explainable AI could help expose problems with otherwise black box models where there is discriminatory decision making. But do you think there is still risk involved with explainable AI, or that it's just not the single solution to that problem of discrimination, perhaps?
Definitely risks, are there, and there's actually quite a few of them. Now, it's difficult to answer this question while remaining at a high level, but I will try. I think in principle, yes, it is possible that generating explanations without thinking about the way in which, without carefully thinking about the way in which these explanations are produced might actually have unintended effects, right? How to mitigate these effects? Well, good old engineering practices, I suppose. That's where I would start from. So making sure that, the algorithms that we use are actually suitable for the task at hand, right? Making sure that the whole pipeline does not exclude subgroups to begin with, right? Because in most cases, for instance, biased explanations come from biased models, which come from biased data sets, right? So when it comes to these issues, one needs to take a broader look, right? One needs to have a bit of a more of a sort of framework approach to the problem, right? Because it's actually difficult to pinpoint, and just isolate, oh, this is when the sort of discrimination happened, right? Or this is when things went wrong, right? Typically, there's a whole pipeline and things can go very wrong at different stages. But again, I think my view is that with explainable AI, as Callum just said, we can actually try to unearth some of these issues, but at the same time, we should be very careful. Sort of over reliance on explanations is also very dangerous, right? Because these explanations, in most cases, at the end of the day, are generated using the same computational methods that are used to train the models, right? So if models are faulty, I don't see why explanations should not be or could not be faulty, right? So obviously, it's a bit of a sort of chicken and egg problem, I suppose. But I think having safeguards at each level kind of it's definitely helpful.
Right. I think we've otherwise covered the questions that we've received, though definitely set me straight if I'm wrong about that. But I wanted to take the opportunity to ask Matt another question as well, because we had to skip through some of the conversation quite quickly earlier on. And perhaps this will give you an opportunity as well just to reflect on where you think you're going to go in your own engineering practice with explainability next year. But I think one of the things we considered earlier was like the different perspectives of what explainability is. Like in your work, I guess, because you're using neurosymbolic methods, you have the symbolic component, which is itself in some way inherently explainable, and then you're still trying to understand with other techniques the neural parts of the systems you're building. Are there particular explainability techniques, the post hoc techniques, which you're interested in applying more as an engineer, or just interesting strategies you've come across recently?
Yeah, I think one of the things that we're talking about a bit is we have this structure, and there's still the step of we might want to use a statistical model to do an evaluation. What I keep saying is this like fuzzy match of an input data to a node. So in the example where we're asking, like, is this person who's applying for a loan over 18? Maybe they have provided some information that isn't clearly them stating, here's my date of birth or here's my age, um, but which might have indications uh, for them being over 18. So, for example, maybe we, for some reason, have a marriage certificate and they got married more than 18 years ago. It would be nice for us to be able to fuzzy match this evaluation of is the user over 18 with that piece of data that's not explicit about it. But when we do that, we're then bringing in this element of having these statistical models and doing things like some of the uh, understanding of what interpretive leaps those models are making um, becomes an area that we're interested in. So for one thing is if we're using something like an LLM to do these evaluations, can we derive a somewhat structured reasoning process on the fly that then lets us basically describe steps that we want to go through and then do those smaller evaluations? Can that form basically a like on the fly reasoning extension to these leaf node evaluations? That's one thing that we've been exploring and are quite excited about. And then there are even just the things that Francesco was describing earlier, of just the good old-fashioned classifier models for some of these things and being able to generate counterfactual explanations over those. And I think those are definitely areas where, again, you strike this nice balance of the neuro and the symbolic techniques, and you can get more useful explanations, more robust explanations out of these things.
Right. And in our last minute or so, Francesco, is there anything you'd like to say about where your research is going next year? Or I also know you have an interest in collaborations with industry. Do you anticipate any particular developments in the next 12 months or so?
So what I'm looking at the moment is consistency, which is consistency in the context of LLMs, VLMs, and all the other LMs. So, we're using these models for many interesting things, but basically you ask the same question twice, you get two different answers, right? And while this might be acceptable in some contexts, I'm pretty sure there are other use cases where you really don't want to see this behavior. So I'm actually looking into this kind of dynamics. The other thing I'm very interested in is sequential decision making, right? So how do we generate explanations for AI models that are used to effectively plan, right? So you have AI models that produce decisions over extended horizons, right? And now how do we generate explanations for these models? So these are just two examples of things that I'm very excited about. There's more, but I'm conscious of time, so I will stop here.
Well, at that point, I shall recommend that people go and look up the Center for Explainable AI at Imperial, and I will post a link in the chat just because it's a little bit too long for me to say. But also, you can find out what we're doing at the research lab at Unlikely if you go to lab.unlikely.ai. But otherwise, we are right on time. So I'll thank our audience for joining us, and thank you very much to Francesco and Matt for talking with me. I think it's been a really insightful conversation, so I hope everybody else has enjoyed it too. And I look forward to more conversations like this. Thanks, everyone.
Thank you.
Thank you, guys.